Welcome to this Focus In video. Today, we'll be looking at optimization. This can be a tricky topic for many people because these problems require you to think a bit more than normal. If you aren't aware, in these Focus In videos, I'll be going more in-depth and more slowly than the review videos. First, before we jump into the calculus, let's review some formulas that come up a lot during optimization. These may seem a little bit basic, but it's never bad to review. So we'll start off with the rectangle, as you can see here. If the rectangle has a base of b and a height of h, then the area is b times h. Remember, the area is the space enclosed by the rectangle. And to find the perimeter, you take 2b plus 2h, or 2 times the quantity of b plus h. You can think of the perimeter as the amount of fencing you would need to enclose this area. And you basically just add up these four sides. If you have a square, that's the same as a rectangle, but the base and the height are the same. Now, let's talk about rectangular prisms. To find the volume of a rectangular prism, you multiply the length, the width, and the height. You can think of volume as the amount of water you could put into the rectangular prism. Next, we have a cylinder. To find the volume of a cylinder, you use the formula pi times the radius squared times the height. Notice this is just the formula for the area of a circle, but you just multiply by the height at the end. If you have a cone, to find the volume, we use the formula 1/3 pi r squared height. Notice this is the same as the formula for the sphere, but just 1/3 of it. Next, we have some right triangle formulas. First is the Pythagorean theorem. The side opposite the right angle, C, is the hypotenuse, and the other two sides, A and B, are the legs. The Pythagorean theorem says that if you add the squares of the two legs, you get the square of the hypotenuse. A squared plus b squared equals c squared. Then, if you have an angle theta, like we have here in red, you can use the sine of the angle, we can use the sides of the triangle to define sine of theta, cosine of theta, and tangent of theta. On the other hand, if you have the length of the sides and you want the angle, you use these inverse trigonometric functions at the bottom. Finally, when you're talking about a person or an object moving, you can use this formula, d equals rt, where d is the distance, r is the rate or speed, and t is the time. So if you take the speed multiplied by the time, you get the distance they move. I know we're spending a lot of time on these formulas, but they will be useful going forward. Now let's move on to the main event. What are optimization problems? Well, they're a type of problem, usually a word problem, where you have to maximize or minimize a quantity. Maybe you have to minimize the cost of something, or maybe you have to maximize the volume of a shoebox. Next up, we'll look at the steps to solve an optimization problem. First, read the problem and make a list of the knowns and the unknowns. A bunch of problems also include something that I call a hidden known. This is something that they don't explicitly tell you, but that you can figure out. For example, if you have a right triangle and they give you two of the sides, you can figure out the third one. The third side would be the hidden known. So, once you've made your list, then you draw a picture. Make sure this picture is a big boy. Don't do any of those mini drawings in the corner of your page. Make it large. Then, assign some variables in your picture. Then, write equations. These equations should relate your variables to your known values. However many variables you have, that's how many equations you want. Since you'll have multiple variables, you're going to have to solve the system of equations for the variable you want. Then you take the derivative and set it equal to 0. This allows you to solve for the unknown variable. Now you might be done, or there may be some extra very trivial steps at the end. Now let's look at a basic example. You're building a rectangular fence around your garden to keep the annoying kids off your lawn. You have 120 feet of fencing. What's the maximum area you can fence off? Okay, so first, we'll make a list of the knowns and unknowns. We know that the perimeter is 120. That's it. Our unknown is the area. Next, a picture. So it's a rectangle because it's a rectangular fence, and our sides are x and y. X is the width, and y is the length. Now let's write an equation. We know that our perimeter is 120. Using the formula for the perimeter of a rectangle, twice the width plus twice the length, we can say that 2x plus 2y equals 120. Now we need to solve this for one of the variables. I'll solve it for y, but it doesn't really matter. I can divide both sides by 2, and I can subtract x to get y equals 60 minus x. We want to find the area, which is length times width. Since our width is x and our length is y, our area is xy. That's the quantity we want to maximize, right? We want to maximize the area. Now, before I can take the derivative of this, I want the area in terms of only one variable. Since y equals 60 minus x, I can replace that in my area equation. Now my area is in terms of only one variable, x. The next step is to take the derivative. Doing that using the power rule gives, now on a new line, we set it equal to 0. Always do this on a new line. So 60 minus 2x equals 0. We can add 2x to both sides and divide by 2 to get x equals 30. Now, before we find the area, let's quickly check if this is a minimum or maximum. If we draw a number line and put x equals 30, and then we can plug in a number on either side of 30 into the derivative to see if it's positive or negative, we'll be able to quickly check if this is a maximum or minimum. So, if we plug in a number more than 30, like 10,000 for example, into the derivative will be 60 minus a huge number, which is going to be negative. If we plug in a number less than 30, like 0, then the derivative is going to be 60, which is a positive number. So at 30, the derivative switches from positive to negative, so 30 is a relative maxima. If you didn't realize, we just used the first derivative test to show that that's the maximum. Okay? Now that we know it's the maximum, we can find the area. So now we know that the maximum width for the rectangle is 30. And since from step 3, the length is 60 minus the width, the length must be 60 minus 30, which is 30. And then finally, we wanted the area, which is x times y, so 30 times 30, or 900. With 120 feet of fencing, we can enclose a maximum area of 900 square feet. I know that wasn't easy, but hopefully you can see that I'm just following a logical sequence of steps. Now, let's move on to another example. A circle with radius r is in the xy plane. The maximum area of a rectangle inscribed in the circle is 2. What is the radius of the circle? Okay, so let's identify our knowns. All we know is that the area of the inscribed circle is 2. We don't know the radius of the circle. Now let's draw a picture. The area of this rectangle is its width times its height. The width is 2x, and the length is 2y. So the area is 2x times 2y, or 4xy. Now we're talking about the maximum of the rectangle, so we want to take the derivative of this equation. So we want it to be in terms of one variable. To do that, we use the Pythagorean theorem. This triangle, x squared plus y squared equals r squared. Solving this for y gives that y is the square root of r squared minus x squared. Plugging that in for the area gives, now we'll take the derivative of this using the product rule. You'll notice I've simplified it to make life easier. Now on a new line, we'll set this equal to 0. If this is equal to 0, then the numerator has to be equal to 0. Solving that for x gives, I'm running out of space, let's go on over to the next page. Okay, so since y is the square root of r squared minus x squared by the Pythagorean theorem, and we know that x is r over square root of 2, we can figure out y. So y is also equal to r over square root of 2. Now we're almost done. Since from before the area is 4xy, we can plug in r over square root of 2 for x and y. This way, the formula for the area is only in terms of r. This is nice because r is our unknown. The maximum area is 2, so we can set 2r squared is equal to 2 to find the radius. Solving this gives r equals 1. So, in a unit circle, the maximum inscribed area of the rectangle is 2. Pretty cool. Now, we have a slightly more challenging example. An island is 2 miles due north of its closest point along a straight shoreline. A visitor is staying at a cabin on a shore that is 6 miles west of that point. The visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to to minimize the time it takes to reach the island. So, we know the island is 2 miles from the shore, and the cabin is 6 miles to the west. And we know the speed of the visitor on land and on water. What we don't know is how much they run and how much they swim. Now let's draw a picture. I obviously didn't come up with this myself. This problem actually came from an OpenStax textbook, and they had this wonderful illustration to go along with it. So, now let's make our equations. Let's say they run x miles, and then they swim y miles. We know the distance equals rate times time. If their distance is x, and their rate is 8 miles per hour, then their time running is x over 8. Similarly, if they swim y miles, and their rate is 3 miles per hour, then their time is y over 3. If we add these two times up to get the total time, we get x over 8 plus y over 3. That's what we want to minimize. To do that, let's get it in terms of one variable first. We'll use this triangle. The total distance here is 6 miles. So if this is if this is 6, then this is 6 minus x. That gives us a right triangle, and we can use the Pythagorean theorem here. If we solve this for y, we get this. Now, we can substitute that in the equation for time. Now the time is in terms of one variable. To find the minimum time, we'll take the derivative. Doing that, we get this. Now on a new line, we'll set this equal to 0. Now we need to solve this for x, and I've shown you the steps there in case you're interested. Anyways, once you do that, you get two positive solutions for x. So which one do we choose? Well, 6 plus 6 over the square root of 55 is around 6.8 miles, but this distance is only 6 miles, so that can't be right. Therefore, our answer is 6 minus 6 over the square root of 55 miles, which is approximately 5.191. Checking by the first derivative test shows that 5.191 is indeed the minimum. So that is the distance we need to run before turning and swimming the remaining distance to get to the island in the minimum time. Finally, this problem is another step up in difficulty. Even though the problem is harder, the steps will be the exact same. We're building a box such that the base length is 3 times the base width, and the box can hold 60 cubic centimeters of liquid. If the material costs 50 cents per cubic centimeter on the 4 sides, and $1 per cubic centimeter on the top and the bottom, find the dimensions of the box that will minimize the price. Let's start by making a list. Okay, so we know that the length is 3 times the width, the volume of the box is 60 cubic centimeters, and the price is 50 cents on the sides and $1 on the top and the bottom. Our unknowns are the dimensions of the box, so the width, length, and height. Now, let's draw a picture to represent this. Okay, here's my picture. So, if my width is x, then my length is 3x, since the length is 3 times the width. I don't know anything about the height, so I'll just leave it as z. Here, the blue rectangle represents the top, and even though you can't see it, there would be a blue rectangle on the bottom as well. Now to write my equations. First, I want to figure out how much red area there is. I'll find the area of each of the rectangles separately. This first big one has a length of 3x and a height of z, so the area is 3xz. There's also another one just like it on the back. For the one on the left, it has a width of x and a height of z, so its height is its area is xz. There's another one like that on the back here as well. Adding these 4 rectangles gives me the total area of the red part. Since the price of the red part is 50 cents per centimeter, to find the price of the red, I'll multiply the area times the price. So I have 8xz square centimeters, and at a price of $0.50 per centimeter, the price is $4xz dollars. Now the blue. By the way, in case it's not clear, the reason why we're finding the red and blue areas separately is because the price for those segments are different. The area of the blue is $1, so the price of the blue is $1 per centimeter, and the price of the bottom is half $1 per centimeter. Anyways, so for the blue, the area of the top blue section here is x times 3x, or 3x squared. Remember, there's also another section on the bottom that's blue, so we need to add that too. So the total area of the blue is 3x squared plus 3x squared, or 6x squared. The price is $1 per centimeter, so multiplying gives us 6x squared dollars for the price of the blue. The total price to make the whole box is the price of the blue and the price of the red, which is 6x squared plus 4xz. We want to minimize the price, so we want to minimize this equation. But it has two variables, and to take the derivative we only want one, so let's change that. I'm running out of space, so let's move on to the next page. So what information have we not used yet? All the stuff about the volume. The volume for this box is the length times the width times the height, and we know that is equal to 60 cubic centimeters. The length is 3x, the width is x, and the height is z, so multiplying those gives us 3x squared z equals 60. We're setting it equal to 60 because we know that the volume is 60. We're given that here. Let's now solve this for z to substitute it into the top equation. Now plugging it in and simplifying gives us an equation to minimize. To do that, we'll take the derivative. We'll use the power rule here. Now on a new line, we'll set this equal to 0. Solving this for x gives that it is approximately equal to 1.882. You should store this value in your calculator to get an exact answer in the end. Now if we do the first derivative test, you'll see that if we plug a number smaller than 1.882 into the derivative, we get a negative number. And if we plug in a number bigger than 1.882, we'll get a positive number. That means that 1.882 is a relative minimum. If x is 1.882 centimeters, the price will be minimum. Now let's find out the rest of the dimensions. From before, we said that z equals 20 over x squared. So if you plug in 1.882 for x, we get z, which is approximately 5.646. Make sure this is stored in your calculator too. So to get the minimum price, the width must be 1.882 centimeters, the length must be 3 times the width, which is 5.646 centimeters, and the height is also 5.646 centimeters. Those are the dimensions that will minimize the price, and we are done with the problem. Hopefully this dive into optimization helped you understand, and hopefully it opened your eyes to the real-world applications of calculus. I'll see you in the next video. Goodbye.